or is it boring? It's good? Okay. It's boring? I can speed it up.
No. Just right on.
So there's a number of, what I love about algebra is it contains all kinds of other fields, kind of merges some other fields, and you have a lot of counting arguments that are conducted or performed in algebra class. And here's one. If you have a cyclic group with n elements generated by A, and you have a B and G, and B is one of the powers of A, which it has to be, right, because it's a cyclic group, then B itself generates a cyclic group H of G, and I can tell you how many elements there are going to be in that H. There's going to be n divided by D elements in that H, where D is the greatest common divisor of n and S. So that order pair means greatest common divisor. And you also have a relationship when two cyclic subgroups are going to be the same. And that's when the greatest common divisor of S and N is the same thing as the greatest common divisor of T and N. So for example, if you have G equals Z6 and B is 2, then the cyclic subgroup generated by B has 3 elements in it. The order of the big group is 6. Now, of course, how many elements do you have in the cyclic subgroup generated by B? Exactly 6 divided by 2, right? And the greatest common divisor of 6 and 3 is going to be 2. So it worked out just the way it's supposed to be. And you have the S2. S is 2. You can calculate it. And you get the greatest. So I'm just testing out and showing you that the theorem works for one example, which I always recommend you do when you have a theorem. So one of the things that, if this is your second time taking it, always as you're reading, ask yourself, can I come up with an example of that? Start coaching yourself. If you can't come up with the example of that, you probably have more of a surface knowledge of what you had from the first time you took the algebra class, which is okay, because that's the way I did it too. And it's part of it, I think. You have to have that surface feeling first for it, and then you see the other pieces come into place. A corollary to this is that if G is a finite cyclic group of order n, and all other generators of G are of the form of A to the S, then it tells you what all the other generators have to look like, where S and N have to be relatively prime. So what can you do with this? Well, you can start counting. So if you have Z18 and you know it's a cyclic group, then you can find all the subgroups and give what we call the subgroup diagram. So I'm going to walk you through how to do this. So the first step is to find all the generators of Z18. So n is 18. So what you need to find are the relatively prime positive integers. And those are the ones that have no common divisors with 18, other than 1. So list out all the elements from 1 to 18. And find all those elements that are relatively prime to 18. I've circled them. If they share a common divisor other than 1, they're crossed off the list. By the previous corollary, these circled ones are the generators of Z18. Now you use the uncircled ones are. So now you use those found generators to develop the subgroups. So the first two are obvious. You have one with 0 and you have one with the whole group. Those are 2 of them. Then all the other generators. So go back to that list. These highlighted elements are your other generators. And you start writing them down. So what is the generator with 2? Well, write them out and see what you get. And I got tired of doing that, so I just went to Excel and just spit them out. And you see I have all these different columns with, I took all the greens and I just added mod 18 because I didn't want to do it by hand. I was lazy. So I just went in Excel and used the mod function and modded by 18. And I just checked in this, I'm sorry, I gotta walk. I just checked when I ended up at 0. And what you notice is some of these subgroups are repeated. So I can cross them off the list. Totally, you can totally do this by hand. But you know, I program a lot, so as soon as I find a way, I just go to the computer and get it to do the rest for me. Is it clear what's going on now? I just went to and took those green elements and added them over and over and over mod 18. So, for example, I'm going to cross off some of these. If you look at this subgroup here, cyclic subgroup, it's the same as this one. Because the 4 appeared here, and then I have this same groups. These are the same elements, just rearranged. So this column here is not a new subgroup. So it's off the list. So this is how I'm using brute force to find all my subgroups. So I just crossed out all the duplicates. And this is what I was left with. I was left with 4 subgroups other than the trivial group and the whole group. I got 4 total subgroups. One is generated by 2, one is generated by 3, one is generated by 6, and one is generated by 9. And of course my 2 that I immediately have for free. So now how do you draw the subgroup diagram? The divisors of Z18 are 2, 3, 6, and 9. And those were my distinct generators. And here's how it works. It's a weird way to do this, but they're all set containment. So this subgroup, if you go back and look at your original one, was contained in this subgroup. 2 was the long one. And this one was inside the other one. It wasn't the full of 2, it just had some of 2. And this subgroup is the trivial subgroup, and it's inside that one for sure. And it's also inside this one because the trivial subgroup belongs to any one of them. This subgroup was pretty small, but it was inside this one. And this one was the big one. This is all of G. So all of this has containment as you go inside. So this is what's called a subgroup diagram. And one thing I want to mention is in the book, it wasn't clear, like he has the subgroup diagram, but it wasn't clear where it came from. It's just a diagram on one of the pages in the book. So this is where you list out all your subgroups and you look at how they're contained and you make sure the containment goes up this way. And that's what he was doing. All right. Clear? Okay, are there any questions?
Always containment from bottom to top and from left to right.
Mm-hmm.
Can you explain what you did in the diagram in the previous one?
So I did actually. I copied and pasted this. See this little piece here? So for example, if you look at 2 has a lot of elements in it, right? And I forgot what was underneath 2, what I had placed underneath 2. It's almost like you had to look at what you have right here. The cyclic subgroup generated by 6 is inside the cyclic subgroup generated by 2. And I can see that right over here.
I mean,
This one is inside this one.
What is the top row and the...
This one?
Yeah, what does it represent? The 2, 3,
Well,
4, 6?
these were my candidates to start adding mod 2, right? All the green ones, those are the ones that are not relatively prime, were my candidates to go and start adding and see what I get. Is it clear now? Bye.
And on the top, the element 18 is the mistake is like 0. Why do you have it up there?
It doesn't matter if I do it or don't, right? It has common divisor, 18 is going to be crossed out. 0, so I don't have to worry about it.
But 18 is not an element of the group.
Yeah. This was just a list of numbers from 1 to 18. Those were not elements of the group. All right, any other questions? All right, tired people. We will stop there.